In this video, we are going to look how to put together everything we've learned into one convolutional neural network. A lot of this stuff, remember, is going to work for regular neural networks as well. I am going to focus on convolutional neural networks because that's what this lecture is mostly about. But by no means are you restricted to convolutional neural networks with these techniques. So let's say we've got our input image now, which is going to be 64 by 64 by 3. So the height and the width are 64. And then you've got 3 color channels. The first layer might look something like 32 by 32. And then we get 16 of these color channels. So usually we are going to either keep the image size the same or the feature map size the same, or we will halve it as long as that's possible. So when we have 28 by 28 image, that's going to become a little bit more difficult at some point, but because 64 is a power of 2, then we can just go half, 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 which is what we're going to do in this case. So now we're halving again to 16 by 16 in terms of the spatial size and 32 channels, which is in this direction. And we can keep going until we get smaller and smaller feature maps. And now we're down to 4 by 4. And then finally, once we get to this sort of size feature map, these are just going to be like a 2 by 2 square. So we can quite nicely convert from this to just a 1 by 1 feature map, which is here. And then we have 128 channels, which all of a sudden can become a 128 dimensional feature vector. So this is your output vector. Or if you've got 10 classes, you can convert this down to just a 10-dimensional vector, depending on how many classes you have, depending on the problem that you are trying to solve. So one thing that I do want to put across, I've spoken in the past about how we're using these kernels, and that makes sure that we consider only local information. So we're not, from stuff around the eye here, we're not considering stuff in the background or the cushion the dog's sitting on or anything like that. That can become a problem because, of course, to determine that this is a dog, we also need to think about the positions of these relative to other objects in the image. So it's important that we can see that he's got 2 eyes over here and then a mouth down here, a little moustache and beard as well. It's not enough to just focus on the local stuff. So this is why we don't go straight from this point to the feature vector. We are going to create more and more expressive feature maps because when we have this kernel here, or this filter here, I should say, which considers all of this stuff, and that moves across. These are representations based on the previous kernels, so this is now a combination of those representations. So you start to link up stuff that's a little bit further away from each other. So maybe with this one, the kernel can see stuff that combines this square and this square. So you get that in this image, in this channel. And then in the next layer, you go even further. So now when you do this with the new filters, you're combining stuff which is even further apart. So maybe now you can see stuff that's this far apart. And it's going to be the same thing as we get further and further down this network, that we can sort of understand stuff that is further distance apart from each other. Okay, so we end up with this 128 dimensional feature vector in this case, but remember this number of channels is something that you control, so you can make it whatever you want to be. And this is our representation of the input image. So if you remember back to lecture 4 when we talked about how we're trying to find new representations of data, you can think of all neural networks or all machine learning really as representation learning. So we're just trying to find new ways to represent the input images that we've got, the data set that we've got. And this is going to be our representation. So this is the thing that we are trying to optimize. We're trying to make this representation as descriptive as possible. And yeah, like I said before, we can reduce this to 10 dimensions if we feel like, if we've got 10 classes and that's what we need. Or if we have n classes, then we just make it n dimensions. So I'm now going to jump into a little bit of code and how you can combine all the stuff we had before. So just before I do, remember that in this section where we have this arrow, we're going to have a ReLU function. And then we're going to do some of our other operations that we've talked about in following videos. So we might do batch normalization, we might do dropouts. So for convolutional neural networks, dropout is going to eliminate some of these channels. So maybe it gets rid of the first one and then this one and then this one. That's all that dropout's going to do, just completely eliminate some of the channels that we've got. And maybe we're going to do max pooling in order to get, so drop, batch normalization, and then max pooling or altering the stride size in order to get from 32 by 32 to 16 by 16. So max pooling. So yeah, let's take a look at that now. The code we're going to look at is within Google Colab, which I will explain to you in one of the practical sessions. And the code is from one of these practical sessions, so you will see something very similar to this. We're just looking in Keras for now. So if you want to use PyTorch in your projects, by all means do, or if you want to use TensorFlow, feel free. To keep everything simple, we're just going to use Keras, and we're going to import some of these layers like dense, dropout, flatten, conv2D, two-dimensional max pooling, and also batch normalization. So this is all just from Keras layers. And I'm going to show you just what the network is going to look like. Quick note that these are going to be some of the hyperparameters that we might want to tune. So if we're using batch normalization, the batch size could be quite important. Also the number of epochs could be quite important, so we'll come to that later. The model here, we just start off by opening this, by suggesting that this is going to be a sequential model, and then we just model.add a conv2D layer. We're starting off by defining the number of channels, so that's going to be the dimensionality down here, so how many channels we're going to have. Kernel size 3 by 3 we've talked about in one of the hyperparameters videos. the activation that we're going to use is going to be ReLU, but you can look at other activations like leaky ReLU or Tanch or anything like this. And for now, I'm going to keep padding the same. So if this is the input image, you can see we're going to try and mirror this network. So you can see that the size from the input image to the first layer is going to be the same. So we're defining padding equals same, and that'll tell the network to put as much padding in as is necessary to keep the dimensionality the same. So you can see in the output that we get here that conv2D, after the conv2D, the output shape we get is 28 by 28 with 16 channels. And we're actually going to be using the MNIST dataset, which starts off as 28 by 28. So that's exactly what we want to see. So the green, I'm going to suggest, maybe I'll write it in green. The green is going to be just the convolutional parts of this network. And then the blue, I am going to have all the different processing stuff that we might need. So that's going to include some batch normalizations, some dropout, maybe max pooling, maybe not max pooling. We'll talk about that later. So in this case, I've added batch normalization, which usually improves performance, and I've added dropout to help us protect against overfitting. Now I've added max pooling to reduce the size from 28 by 28 to 14 by 14. And this is what happens here. So you can see that that's had the desired effect. Quick note, there's quite a lot of debates whether you should use batch normalization or dropout first. For me, we're just learning how to apply neural networks, so just do whatever seems to get the best results for you. Don't worry too much about this. There's still a lot of debate, so one's not definitely superior to the other. This time we are using a stride size of 2, and that's going to reduce the dimensionality of the feature map. But notice that we didn't use this padding equals same. So it's actually gone from 14 by 14 to 6 by 6. So at this point, after we've done the max pooling, we've dropped down, we've got to this stage, like the top of this layer. And now we want to reduce stuff down to here. So we are going to, one way that we can reduce the dimensionality is having stride size of 2, but alternatively we can get rid of this. Actually, first I'll just show you, if we have padding equals same, then we will get, instead of going from 14 by 14 to 6 by 6, we should go to 7 by 7. So that's exactly what we've got here. But we can eliminate this stride and instead do the max pooling. Okay, and now we're getting this 7 by 7 afterwards. And this is just going to be exactly the same thing. If we want to double the amount of channels but reduce the size, we're going to do this exact same process another 2 times. So let's do that, see what happens. And you see we get from down to 3 by 3 to 1 by 1. We don't really need this additional 1 by 1 stuff, so let's get rid of the max pooling there and just flatten directly from here. So once we've gone from these vectors to tensors, so once we've flattened this bit, we can, maybe not an arrow, once we've flattened this part, we can just do a dense layer rather than a conv2d layer. So this is a fully connected layer from the neural networks. And we can again use dropout. And then finally, we've got 10 classes. So we can just use 10 here if that's easier. But we just do a final layer to get to the number of classes. And notice that we've switched our activation function to softmax rather than sigmoid or rather than relu. So for more information on that, see the activation and loss functions video. So let's run this. And you can see we've got a reasonably deep network now. So let's compile and try to run things. Okay, that's a good start. So the first thing, because we've got quite a deep network, you can see that we're reasonably slow to train. And the last main thing that I want to show you here, as our accuracy increases, is that currently we're just running on a CPU, but what we can do is use Google's cloud server to connect to their GPUs. So we go to hardware accelerator. Sorry, I should show that in detail. We go into edit, then notebook settings. Hardware accelerator is going to become GPU and save. That's going to stop everything. So now let's just runtime, run all. And then this will just run everything within our notebook. And you should see that this will train a lot faster now. So this is doing a much better job already. And you can see that we're maxing out at about 90% accuracy, which isn't that good. It's not bad, but it's not particularly good. And the test loss is 92%. So we can see that something really good is happening, that we're not overfitting, which is really, really important. So what we might look to change is to instead increase the number of epochs that we're trying to use. So we're going to go from, instead of having 12 epochs, we're going to use 100 epochs. So let's try again. And this time the accuracy of our model during training is moving forwards towards 100. So in this case, all we needed was additional training time. And this is going to be what a lot of the work that you do is actually comprised of. So what we'll spend a reasonable bit of time doing is trying to work out whether this dropout 0.3 is optimal, or should we be using dropout 0.1? Are we overfitting? Or are we just getting rid of too many of these channels, which is causing performance to be a lot worse? Maybe it's the opposite. Maybe we're overfitting and we need to increase dropout. So there's loads and loads of trial and error involved at this stage. It's up to you, like how much you want to go into depth, trying lots of different things. But this is what the iterative development mission is going to be about. Try messing around with the number of channels. Oops, these should be 64 and then this should be 128. So maybe we'll see if there's any difference there. When we try again. But we get to 97% accuracy. And again, test accuracy is also going to be 97%. So we can just redo this model and try to compile and fit again and see what happens this time. And you can see that we get to 80% a lot faster than we did before, and maybe we're even getting to 98% as early as the 35th epoch just by adding more channels later on. So you can see some of the different things that you can try, and that can really improve your performance. So play around with this and see how it goes. just to sort of understand what's going on at these different layers, is that you'll have something very simple like edges in the first layer that you have. So if I go back up, so at this stage, after this stage, you're just going to have very, very simple features like edges, and then as you go deeper, then you'll get some like contours and some corners where you combine, if this is one of the features in your first layer and this is another feature, now these features are going to be combined in the second layer. And as you get deeper and deeper, then you are going to have more of the complex stuff, because now you're combining second layer features, and then in the fourth layer you're going to combine third layer features, which is why you want to use more of these channels, because there's more different combinations of those features than just a one-to-one mapping. So let's try testing again, and test accuracy actually decreases, so that would suggest that we're overfitting. So now what we would go back and do is try to increase the dropout and see if that improves performance. So that's everything for this video. I hope that is clear, and I hope you have some understanding of how you can play around with your network, engineer it to get better performance. We could have seen that it's dropping because our validation accuracy here is actually reduced from our training accuracy. So maybe we could have noticed this at an earlier point and stopped training, and then tried something else. That's going to be relevant if you have a different data set which is going to take longer to train. But in general, I hope you can see how we play around with neural networks and how real-life machine learning engineers are building their algorithms to squeeze out the last few % of performance so that these things are reliable enough to be used in the real world. That's all for this video and all for this lecture. So I'll see you in the practical sessions, and next week we'll move on to some more of the advanced AI. So see you then.